So here edge triggered flip-flops. In basic master-slave flip-flop, master is enabled during the entire period the control input is 1. So this can cause in zeros and ones catching. To avoid the zeros and ones catching, signals on the information lines are restricted from changing during the time whenever the master is enabled. Also a delay in the output, since master state is established during the positive edge and transferred to the slave on the negative edge of the clock. That is, whenever the level is 1, the content of the master is changed. Okay, so the master is enabled whenever the clock signal is 1. The content of the master is transferred to the slave whenever the control signal goes from 1 to 0. 1 to 0 means negative edge. Edge triggered flip-flops use just one of the edges of the signal. This is referred to as triggering edge. Now here we have a pulse like this. This going edge is known as a positive edge. This is known as a negative edge. So edge triggered flip-flops will be triggered only on the positive edge, only on the negative edge. But whereas in the master slave flip-flops, it will be triggered on the levels. This is the level, this is the level. This is level 1, this is level 0. With respect to pulse triggered, we talk with respect to the master slave flip-flops. Whereas edge triggered, we talk with respect to positive going edge, okay, and negative going edge. So positive going is this, negative going edge is this. The output responses only on the positive going edge if it is a positive edge triggered flip-flop. The output responses only on the negative edge if it is a negative edge triggered flip-flops. In edge triggered flip-flop, we have two types of flip-flop, positive edge triggered, negative edge triggered. Okay. Response to the triggering edge at the output of the flip-flop is almost immediate. Okay, but still it depends on the propagation delay which will be specified by the manufacturer. Once triggering occurs, flip-flop is unresponsive to the information input changes until the next edge. The flip-flop will change only on the positive edge or on the negative edge. It will not respond on other times. Other times it will not respond, that is unresponsive. The output will respond only on the positive edge and on the negative edge. Okay. So here this is a positive edge triggered D flip-flop. Okay, what is this, student? This is S bar R bar latch. You know, I have already taught you the S bar R bar latch. Okay, and these are some NAND gates connected. The output is connected as an input to this. The output of the second NAND gate is connected as one of the input of the first NAND gate. Here if you see. Next, this is a simple S bar R bar latch. And what is this? This is a NAND gate 3, the output of which is connected as one of the input to the fourth NAND gate. Whereas D is a data input which is connected as an input to the fourth NAND gate. The output of this is connected as an input to this third NAND gate. Where is clock? Clock is connected to one of the input to the second NAND gate and is also connected to the one of the input of the third NAND gate. Okay, so here we have the output of the fourth NAND gate is also connected as one of the input to the first NAND gate. So this is the construction of the D positive edge triggered D flip-flop. So its explanation is given in this slide. Whenever C is 0, you can see here, whenever C is 0, what happens? Regardless of the input at D, outputs of the gates 2, 3 are 1. So 2, 3. So if I put a 0 here, this will become 1, and if I put a 0 here, this will become 1. So he is telling that whenever I apply clock is 0, this 0 comes here and this 0 comes here. So output of the NAND gate 2, output of the NAND gate 3 becomes 1. So this one is applied as an input to this S bar, and this one is applied as an input to this R bar. So if S bar R bar is 1, the state of latch is held as it is. That means it retains the present state. Okay. So next assume D is equal to 0. D is equal to 0. So put D is equal to 0 here. Next output of the gate 4 is 1. So output of the gate 4 is 1. So if one of the input is 0, NAND gate output will be 1. Next output of the gate 1 is 0. So this one is connected here. Clock is 0. So what will be the, so when assuming that when C goes to 1, okay, so output of the gate 1 is 0, means here it is 0. Next when C goes to 1, so if suppose this is transited to 1, 0 to 1 changes happen, so this one will come here, right? So this S bar is also connected to this one will come here. Okay, so this one is also connected to here. So all the inputs to the gate 3 will become 1. So all the 3 inputs to the gate 3 will become 1. So output changes to 0. So output changes to 0. Output of the gate 2 remains at 1. Since the output of the gate 1 is 0, output of the gate 1 is 0. So what happens here? S bar is 1, S bar is 1, R bar is 0. So here S bar is 1, R bar is 0. So here output of the gate 3, 0 is fed as an input to the gate 4. Okay. So output of the gate 3 is fed as an input to the gate 4. So output of the gate 4, so output of the gate 4, gate 1 is not affected. So changes to the D. So if S bar is 1, R bar is 0. Okay. So according to the definition of S bar latch, S bar is 1, R bar is 0. It will reset. Reset means Q is equal to 0. Q bar is equal to 1. So we had applied D is equal to 0. As we all know that D flip-flop is nothing but it is also called delay flip-flop or transparency flip-flop. Transparency means what? If D is 0, Q is 0. If D is 1, Q is 1. So the D has appeared to the Q 0. Similarly, when we have C is equal to 0, D is equal to 1, output of the gate 2, 3 are 1. Next, output of the gate 4 is 0. You can see here the output becomes 0. Next, when C goes to 1, 0 to 1, the output of the gate 2 is 0. Here you can see that output is 0. Next, we have output of the gate 3 remaining at 1. S bar is 0, R bar is 1. So what happens whenever D is 1, that time S bar becomes 0, R bar becomes 1. So here what happens whenever S bar is 0, R bar is 1, Q becomes 1, Q bar becomes 0. So it will set. So D was 1 now, Q became 1. So similarly apply the inputs. You very well know the operations of the NAND gate. You also know the operation of S bar R bar latch. You have the explanation in the slide. Just what you do is whenever you apply 0 or 1, just check the inputs and outputs going and just check the Q and Q bar. Ultimately what you should know from this is whenever D is 0, Q is 0, Q bar is 1. Whenever D is 1, Q is 1, Q bar is 0. So here we have edge triggered flip-flop. This one I have already explained in the previous slide. So D is 0, positive edge clock is applied, Q will be 0, Q bar will be 1. When D is 1, positive edge of the clock is applied, D is 1 means Q is 1, Q bar is 0. Irrespective of the D, if clock is 0, it will retain the present state. Irrespective of the D, if clock is 1, it will retain the present state. So you need to apply the clock in order to work this as a edge triggered flip flop. This is a positive edge triggered flip flop. This is the logic diagram of the positive edge triggered D flip flop. Next we have B, that is a function table where Q plus denotes the output Q in response to the inputs. And this is the logic symbol of the positive edge triggered D flip flop. Next, this is the timing diagram of
Ma'am,
the, yes,
ma'am, that
one minute,
if
one
C
minute, one
means
minute.
what ma'am?
So talk about this timing diagram of the positive edge triggered. What is this, students? This is a data, that is a D input. What is this? Clock. So this D will reflect on the Q output only on the edges. This is the positive edge, right? This is a positive edge, this is a positive edge, this is a positive edge. So in the function table we have shown it like this: positive edge 0 to 1, positive edge. So this is positive edge. So when D is 1, when clock is at the positive edge, D is 1, so it is transferred to the Q. Next it will retain up till the next positive edge. So when the next positive edge comes, D is 0, so Q became 0 here. It will retain up till 0, up till when? Up till next positive edge. So the output responds only on the positive edge of the clock signal. Hence it is known as positive edge triggered. They do positive edge. Okay, this is positive edge. Again, see here at the positive edge D is 1. So the D is get transferred. It will retain up till when? Up till next positive edge. ಸೊ ಪಾಸಿಟಿವ್ ಎಡ್ಜಿಗೆ ಅಷ್ಟೇ ರೆಸ್ಪಾನ್ಸ್ ಮಾಡುತ್ತೆ ಕ್ಯೂ ಔಟ್ಪುಟ್ಟು ಡಿಗೆ. ಓಕೆ, ದ ಔಟ್ಪುಟ್ ಕ್ಯೂ ವಿಲ್ ಬಿ ಚೇಂಜ್ಡ್ ಓನ್ಲಿ ಡ್ಯೂರಿಂಗ್ ದ ಪಾಸಿಟಿವ್ ಎಡ್ಜ್ ಆಫ್ ದ ಕ್ಲಾಕ್. Okay, so it will retain that output up till the next clock, positive edge clock. It will retain up till the next positive. I put your arrow mark to show you that it will respond only on the positive edge of the clock. Next, Q is 1 here, Q bar should be 0. Next here Q is 0, Q bar should be 1. So Q is 1, Q bar should be 0. Okay, so this is the timing diagram and this is how you explain the. So here negative edge triggered D flip flop. What is the change in the negative edge? The D flip flop will respond only for the clock when it is going from 1 to 0 transition. When it is going from 1 to 0 transition. So here, if this is a clock, this is positive going direction, this is negative going direction. Negative edge triggered D flip flop will respond only when the clock is growing from 1 to 0. So in the truth table, we'll be talking like this with respect to like this. So this is 1, this is 0, this is a negative edge. So D flip flop will respond only on the negative edge going of the clock. Okay. Simply place inverter at the output, at the control input of the flip flop. It will become negative edge triggered D flip flop. Okay, so next we have positive edge triggered T flip flop. As I had shown you that JK flip flop, I had shown you this is symbol of JK flip flop. If I tie J and K together, it will become T flip flop. Okay, JK flip flop is there, no? If I tie the J and K inputs together, it becomes T flip flop. Now let me tell you the operation of the T flip flop. Whenever T flip flop is 0 and a clock is applied, positive edge of the clock is applied, it will retain the present state. Whenever T is 1 and you apply the positive edge of the clock, it will toggle. Toggle means if Q is 0, it becomes 1. If Q is 1, it becomes 0. It is the meaning of toggle. Okay, so this is another type of construction of the positive edge triggered T flip-flop. Students always remember, with respect to clock I am talking, positive edge means this 0 to 1 going, 0 to 1. Negative edge means this 1 to 0. Okay, when you apply a NOT gate to the control input, it becomes a falling edge. Okay, so this is the symbol of the T flip-flop. Next we have characteristic equations. So next state table. What do you mean by next state table? It shows the value of the next state of the flip-flop for each combination of values to the present state of the flip-flop and the information lines. Now what is it telling? In the next state, depending on the inputs and the present state, we have the values of the next state. That is, what is it? If suppose if this is SR, what are these? Input. Q, what is this? Present state. Q plus, what is this? Next state. So next state table Q plus depends on the present state as well as the inputs. The algebraic description of the next state table of the flip-flop is called the characteristic equation. When we write the next state table, for that we put a K-map and then we get an equation, and that is nothing but the characteristic equation of the flip-flop. It is obtained by constructing the K-map for Q plus in terms of the present state and the information input variables. This will be very well understood when I solve it with various flip-flops. So here I am talking with respect to SR now. Okay, so here this is S, this is R. When both are 0 0, S is 0, R is a 0. Okay, S is 0, R is 0. Present state may be 0 or 1. Whenever S is 0, R is 0, it retains the present state. So if the present state is 0, it will be, next state will be 0. If present state is 1, next state will be 1. Next, coming to this. Okay, so this is 0 0 over, present state may be 0 or 1. Next, when S and R are 0 1, 0 and 1, present state may be 0 or 1. Whenever R is 1, it will reset the flip-flop or latch. Okay, so it will reset. 0 0 means a reset. Next, whenever S and R are 1 and 0, present state may be 0 or 1. Whenever there is 1 on the S input line, it will set. Set means output is 1. Next, whenever S and R are both are 1 1, present state may be 0 or 1. It is undefined, so inputs are not allowed, means it is undefined dash dash. Okay, so you need to put a K-map for this. K-map. Okay, how to put a K-map for this now? So this is the next state table of this SR. And what is this? This is a function table, already I have discussed. S is 0, R is 0, it retains the present state. S is 0, R is 1, it will reset. S is 1, R is 0, it will set. Whenever both are 1 1, it is undefined. So here we have put the next state table for this function table. Okay, S is 0, R is 0, present state may be 1 1, it will retain the present state. S is 0, R is 1, present state may be 0 or 1, it will reset. S is 1, R is 0, present state may be 0 or 1, it will set. 1 1, present state may be 0 or 1, it will be undefined. So I'll just put a K-map here. Q S R 0 1 0 0 0 1 1 1 1 0. So this is 0 0 0. All three are 0 means it is a, what is this? 0. All three are 0. 0. Similarly, you complete the K-map. See here. Q is 0, S is 0, R is 0. This first row. What is the output? 0. So similarly, you complete this K-map. Okay. Complete this K-map, you will get like this. Okay, QSR. For that particular you complete, you group it, you will get Q plus is equal to S plus R bar Q, R bar S plus R bar Q. Okay, so this is the you when you group. See here, this one what you are getting, see, one is here. Okay, so what you are getting here, R bar Q. So R bar Q. For this quad, what you are getting, quad, you are getting S plus R bar Q. This is the characteristic equation of the SR flip flop. Okay, so SR flip flop I have explained now.